Today, we are going to talk about classification, a type of machine learning, and we're going to do so in a way that builds intuition for what we're doing when we do classification. There are two big types of supervised machine learning. Regression and classification are both about predicting values for some dependent variable based on independent variables. Both of these are about using existing or historical data to predict. In regression, we are predicting a quantity. So in the image here, we say, oh, I'm going to predict what score someone's going to get on a test. We're predicting a number in our regression. In classification, we're predicting a label or a category or a class. So I want to say, is this transaction fraudulent or not? Is this email spam or not? Does this person have a disease or not? They're the two main types of supervised machine learning. Let's break it down a little bit more. So in regression, our goal is to fit a line through data that is continuous and numeric in order to understand and predict values. Our output is going to be something that we're predicting. I'm predicting the GDP of a country. I'm predicting someone's salary. I'm predicting how happy they are. If they turned happiness into a number on a scale of 1 to 10, how happy are you? Classification, which we're focusing on today, the idea is to put objects, ideas, or things that we're studying into blocks to understand and predict labels or categories. So our output is going to be categories like red or blue, disease or no disease, spam or not spam. There are tons of machine learning classifiers that we could use. We'll talk about k-nearest neighbors here. So here's an example. Classification is used in real life. If you've ever gotten an alert on your phone from your bank or your credit card that says, unusual activity in this account, go tell us if you meant to be doing this thing or not. Their machine learning algorithm has decided that your activity is fraudulent based on the inputs that you've given it, where you purchased the thing, the amount, the time of day, and so on. So banks really do use this to monitor credit cards. It's probably more complicated than the simple example we'll go through, but this is effectively what's going on. Banks want to know automatically if a transaction is usual, kind of consistent with my everyday transactions, or unusual, and therefore we could assume or potentially assume fraudulent. Banks know a lot about how you're spending your money if you're using a card of any kind. So where am I typically spending money? What types of goods am I buying? What are the values? What times am I shopping? And so on. They also have examples of lots and lots of activities that they know because they're looking back in time were fraudulent. So I know that when someone buys something that is a huge amount, it's more likely to be fraudulent. I know that if something is bought at 4 a.m. rather than at noon, maybe more likely to be fraudulent. What the bank is doing then is using machine learning to look at the historical data from my past transactions and whether or not it was fraudulent to predict the class, the fraudulence of my new transaction. So I have all this data on my previous purchases, and I know whether or not any of those previous purchases were fraudulent. Now I have information on a new purchase. Can I use that existing historical data to predict whether this is also fraudulent? That's what we're doing with classification. We're detecting fraud and other things. The logic of false positives and false negatives applies here. So I could incorrectly call something fraudulent when it's not, or you've experienced fraud and your bank was like, nah, that's legit. Classification is about prediction. We do it to predict values. We want to use the relationship between variables in data that we have to predict outcomes for future observations or interactions. So to say it all one more time, we have a past relationship between our X and our Y. We are going to be presented with these X's for a new observation and predict that Y. So here are the building blocks for building a classifier. So we are going to start with units. So we have some unit that we're trying to understand. So this could be people on a dating app. It could be transactions that we're making with our card. This could be patients presenting at a hospital with a particular set of symptoms. So suppose we're doing a transaction, right? We have observations, transaction 1, transaction 2, transaction 3 that I've ever made in my whole wide life. And we want to make predictions for future transactions. Each observation, each transaction in this case, has attributes. So these are our X variables. You'll also see them called features. You may see them called covariates. And these attributes or features are going to help us predict Y. So in the case of transactions, I might have the geolocation of where the transaction was. I might have the type of good that it was. And I might have how much money I spent. There can be a large number of these. We might have hundreds of attributes. And these observations are in classes, which in this case are binary, perhaps. So a transaction is safe or fraudulent. You could have multiple classes as well. For example, maybe I want to predict what party someone's going to vote for in a general election, or what party a new voter is going to register with. And we might say Democrat, Republican, Independent, Green. Continuing with some building blocks. So we have historical data. The bank has historical data on the relationship between X and Y, both for you and for every other customer that they've got. So lots and lots of historical data. And we already know the inputs and the outcome. And we are going to put most of this in our training set, or what we're going to call the training data, meaning we're going to take some percentage of the data, maybe 80% of the data, maybe 50% of the data that we have, and jam it into the computer and say, look at this. Find the relationship. Our classifier is going to learn the relationship between X and Y in our training set, and it's going to use that relationship to predict the class Y of new observations. Later, we will evaluate the accuracy of our model using the remaining holdout data, that 20% that we didn't put into our training data, and say, hey, here are the predictions we make, and compare it to what is now the test data. We'll talk more about that to come. Generally, we prefer more accurate to less accurate classifiers, though note we don't necessarily want 100% accurately. That could be a sign of overfitting, basically over-tailoring to the past, and therefore making it more likely that we actually will make more errors in the future, even outside of the test set. All right, I'm kind of dropping a lot of vocabulary around. Let me make this more clear by building some intuition from an actual classifier that you can use. If you check out our online textbook, you'll see some code for how you can practice with some examples. The idea with K and N, the name means something, K nearest neighbor. Classify new observations in our data, a new transaction, a new patient showing up at the doctor's office, according to the classifications of the K nearest neighbors in terms of attributes. For example, the red star is placed based on its values for X1 and X2. So the transaction example would say, so X1 is our attribute, the location of the purchase, and X2 is the quantity of the purchase. And we have placed a particular new purchase right there where that red star is. If K equals 3, that means that I am going to count the 3 nearest neighbors and say, hey, what class are they? What category are they? And then assign that category to my new transaction. So if purple is totally fine and yellow is fraudulent based on my historical data, I can say, okay, there are 2 purple and 1 yellow. We are going to classify this new transaction as safe and not raise a fuss or ask for verification or whatever else I would do. If K equals 6, however, the red star is classified as yellow because I could say, okay, the 6 nearest neighbors to are purple, 4 of them are yellow. The majority wins with yellow. So now we would say, fraudulent. So right here, it's up to us as researchers what we want to set that K to. And there are some guidelines for it, but it's largely up to us. This is an example that comes from Inferential Thinking, which is the textbook for the course Data 8 from UC Berkeley, inferentialthinking.com. So this is an example they use of trying to detect a disease. So you could detect something called chronic kidney disease, CKD. A patient shows up in a hospital. We could measure things about that patient, including their glucose levels and their white blood cell count. And we could say, okay, I wonder if this tells us whether or not some patient has chronic kidney disease. But we can zoom in here and we can say, okay, suppose there's a new patient that comes in, our red dot, and presents with values for our 2 variables on the X and Y axes near 0. By the way, if we had more than 2 attributes, a third attribute, we would plot this in 3 dimensions. So we would have a 3-dimensional plot. You can see it in our online textbook, a 3-dimensional plot, and it goes up 4, 5, 6. So we're going to look at the K points nearest to this red patient who shows up with these values in their blood. So let's suppose K is 3, and we take a vote of our nearest neighbors. The majority is our prediction. In this particular case, it's kind of hard to tell, but in this case, our patient is nearest to, let's say, 2 golds and 1 blue, which means they are coded having no chronic kidney disease. Did we get it right? I don't know. We don't know. Our models can have errors, and there's a lot more that we can go down the road with this. But from now on, when you see someone talking about classification, this is kind of what's going on in a lot of cases. Alrighty. See you next time.